learn by compression and build by removal. I have been thinking recently about something that made me do a lot of sense. When I was at high school, or when I was university, they called my class notes the MP3. It was like a friendly name for my notes because of the rate of compressions that I achieve. When we compare at the end of the subject the notes that I had taken with those of some of the colleagues of me, not fully random sample, we found rates of compressions in the realm of 15 to 1, 20 to 1 sometimes, in terms of amount of pages. It was very funny. At that time, the MP3 was very, very popular because it was before streaming became mainstream, very popular. It was, let's say, 2005, around that. Could be the Pike days. It was probably the least funny. It was for the teachers, because I kept staring at them while they did the speech. Sometimes they even dictate the notes, and I was staring at them point blank. And for the least correct teachers, it was very uncomfortable, and it was kind of part of the game for me to making them uncomfortable. But it was not the point. The point was getting to the core of the thing. I wanted to understand what they were trying to convey, where was the main idea, the core truth, and not them writing down only those core truths. The interesting thing is that, well, when people look at the notes and it's okay, we have like 60 pages of notes for this very tough subject, and you have 3-4 of them. What the hell is this? And I would used to say, okay, it's all there. You can look into it. It's no missing parts. And even funnier, some people were discouraged to ask me for the note, for sharing with them, because they simply were not fully rendered in the printers they used to work with. I print the notes and I can't see nothing because it's all brute. It's so compact that I cannot see nothing. It was not about the amount of written down that it was, because it's very small, but the core, the content, it was very, very distilled into very compact notes. The main thing is that doing that forced me to learn while doing, because by trying to discard the superfluous things and come with a compact version, when I was going to study the notes, I didn't need them at that point, because I already learned them while trying to distill the core truths before writing down. This has been very revealing to me, because I feel that I've been learning a lot during my years as a machine learning engineer and data scientist. But I have not been fully aware until recently, because through my practice, through my approach to problems, what I try to do is go to the minimal coding version. When I'm coding, I'm just trying to discard everything that is not needed and go to the minimal core truths again. By doing that, by stripping out of the things not needed, getting to the minimal code base, getting to the minimal concepts required to do that, going to the minimal modules and concepts to have the to have the problem solved. Like Michelangelo trying to chisel out all of the things in the marble piece that are not the sculpture itself. Only by removal you get to the actual statue, the actual piece of art that you want to get into. And doing that through few years, I feel it has been compounding until found that I've been learning a lot, and didn't realize until recently, by connecting these two ideas, these two processes, that actually I was learning coding and machine learning and data science by compression, the same way I was learning through my high school and university years. I was learning by compressing the nodes. Suddenly it made a lot of sense, because I'm not the only one saying that learning is a form of compression. Learning is a process of compression. And well, I cannot but keep on thinking on auto-encoder neural networks architecture for unsupervised learning, where what we want to do is minimize the reconstruction error by trying the neural network to predict as an output the input for that particular data point. But the interesting thing with the learning, because the problem is so easy that it's not a problem unless you add the constraint of narrow the neural network net until being able to project it into a very compact representation with a very reduced dimensionality, which is the core bottleneck of the neural network, where what you want to do is use that as a projection for embed the input data as a compact vector, as an embedded representation. And the stronger the requirement, the harder the constraint, the lower the dimensionality where it is projected, the more learning you distill into the neural network. What happens that when you have this very compact representation, you discard all of the noise of the input data, you discard all of the unnecessary patterns or virtual patterns that you can see in the network, and you go to the core essence of the thing that represents the structure of your data. When you use these embeddings, when you use these compact representations, these projected vectors, you can use them for many other tasks, for many other downstream tasks, unrelated tasks, using this essence, this representation of the data. And you can train a classifier on top of this for some unrelated tasks, because have the core structure, the core truth of your data, and everything which is there. It's something that is not just noise. This leads very easily to the idea of the duality between overfitting and generalization. These two concepts are opposite, but obviously part of the same dimension, which is a common dimension, which is, how could we call it? It's the amount of information that you compress. Overfitting on one side and generalization in the other. They're opposite, but part of the same scale. When people ask you to improve a model, many times they say, this feature, this is a very good feature. And adding something, so not every time is improving the thing that you want to improve. It's not enhancing if you add, not by default, not in general. I like to frame it this way. If your model says that it rains because it is Tuesday, your model is overfitted. Adding the day of the week to forecast to a weather forecast model is not a good idea. And I connect it to the nodes. If you add some nodes, if you add everything to your nodes with the idea of, I don't want to lose any information, I want to place in my nodes all of the things that at some point could be important. If I add to my model any possible feature that the model could somehow learn a new pattern, it could start to reveal and to model better some corner cases. Not always. And it's a very contrarian view. Adding is not always improvement. I had a very funny conversation the other day with a friend of mine, and we were joking about when people try to look for some certainties that they have everything controlled. They do not miss any data point. They have a strong certainty in their models, in their information, in their view of the world. So sometimes even if you give them bad information, even if they know that there is not good information, they are happy because they have something to clench into. You give them a number, they're much more happier because now it's mathematics, now it's pure, it's a number. Maybe it represents nothing, or a fake statistics, or something that a measure that a measure about a magnitude that they don't even understand what the magnitude stands for, but they have the number. Okay. So it's 37% increase. Okay, that's good. I don't know, increasing what or relative to which baseline, but it's 37 plus more. So they are fine. It gets comfort, and the idea is that it expresses, for me, it summarizes how in my experience, I interact with more people, more leaning into this memorization side of the scale, better than against learning. It happens as well that it works for many kinds of learning from many points of view. The more challenging your validation set, the more obvious is that overfitting is not something good. But for the short term, it looks fine. If you look into a not very challenging validation data set, okay. If I add this extra feature, if I complicate the model, if I extend the training epochs, it gets better performance. But once that you measure the model against a more challenging data set, you want to assess a weather forecasting model for not just for the day after, but try to model the whole week. And you will realize that if you look into very specific patterns, your model could improve sometimes in the short term, but it gets beaten in the long term, in the most challenging data set. It happens as well in learning, the same way, a different facet, different point of view. But when people memorize, they could say, okay, I did pass the exam with not much effort. Say, okay, this is a good way, this is a good approach. But this is only if you measure in the short term, because in the long term, you start accumulating knowledge depth, and it compounds very quickly. So yeah, for the next exam, if you need to memorize things for the new one, but keep in mind and memorize and review the data that you memorized for the previous one, and so on, and it keeps compounding. And when things compound through iterations, they do it very quickly. So suddenly you end up with disciplines like it's very cumulative, like mathematics or technical disciplines where everything is built on top of the previous. Memorization doesn't lead you very far, but learning, yes. This duality between memorization and intelligence keeps very stubborn, and it happens in many ways. We could see as well this as memorization versus intelligence, and it frames very much the same like it does for overfitting versus memorization. It's the parallel. There are parallel dimensions for the same thing. It happens the same for building. This simplification in my practice as machine learning engineer, as data scientist, I tend to go in that direction. If I face a problem, if I face a code base, my main idea is to fight aggressively complexity. Because complexity is not sophistication. Simplification is the real sophistication. Just look at the Raptor engine. This famous image about the Raptor engine evolution across the 3 stages. This is wonderful. It comes from a very complex system with a lot of pipes around systems, auxiliary systems of auxiliary systems, and through time the evolution keeps on removing them and end up in a very simple product, in a very system, in a very simple system, which is it's a much better engineering product. It's simpler, it's cheaper, it's more scalable, it's more reliable, less prone to failure. It's just simply a better product because it's simpler. I use that as a North Star for how I approach my professional practice as machine learning and data scientist. This is it's a very good condensed view of how is the direction I like to pursue. But it's not easy. The short term is adding something to your code base that fixes a problem or adds a feature. But in this Elon kind of mental framework, you do not optimize what shouldn't be there in the first place. You do not optimize what should be removed. So I try to find things, concepts, components that should be removed. But the thing is that it's not easy. At the short-term goal, it's always easier to add something and fix the problem and go ahead. But again, it keeps on iterating through complexity. It keeps on compounding through iterations very quickly. And the thing is, what should you be removing is you need to you need to understand the system very well as a whole, very deeply, very intimate relation between you and the system, to understand as a whole what is needed and what is just a superfluous addition, what is core and what is simply something unjustified. This is just unjustified complexity. But you need to go very deep into it and see and understand the system very deeply in order to get to this intimacy, to learn to say this is not needed, and to split the fundamental from the superfluous. And sometimes the Elon thing is that it's not for everyone and it's not for every situation, is that you remove aggressively until you realize that you got too far and you need to put things back into the system again. And that is not for everyone. Some people are more scared of doing that. It's very aggressive for them. And for some products, some systems that are mature and that some other systems rely on them, but you cannot modify them that aggressively without causing massive disruption around. So it's not for everything. However, I try to do that. And for instance, when there is a pull request and it adds no latency, it doesn't decrease the performance, it causes no conflicts with the master branch, it adds a feature that maybe it adds some potential value in the feature, and they ask me to review, and I'd say no, we shouldn't be merging this because it adds code complexity to the code base. And people got puzzled by that. They don't like it. But this iterative natural compounding, like everything which compounds and through iterations, things are in the exponent. They grow up very quickly. This is the final boss. The complexity is the final boss. And it's very hard to fight against complexity because it requires this very deep understanding of the system. You cannot simply live in the surface and try to change things in the surface, because it's difficult to get to the depth, to be able to remove things and get to a better state without breaking anything. But it's one of the things that I realized is most important. It's very contrary view. My experience with the people I interact with, in general, it's very a contrary view that less is actually more. Maybe we go to the Tao and get some of its wisdom. We can say that the value of a pot is that it contains empty space.